The goal of modern edge engineering is building vision language models that can autonomously and physically control a computer's graphical user interface in real time. Standard software approaches break down quickly in this environment. Relying on OS-level hooks introduces fragility. Moving raw frame buffers back and forth across a PCIe bus creates unacceptable lag. And without strict mathematical guardrails, models frequently hallucinate UI coordinates. The Pi IntelliJet VLM architecture bypasses the operating system entirely. It acts as a direct bridge between the unified memory of an Intel Lunar Lake processor and a JET KVM hardware IP controller. Achieving deterministic automation requires abandoning layers of software abstraction. You have to engineer directly at the hardware edge. To understand how this architecture operates, we are going to deconstruct it backward. We will start with a physical result and trace the data pipeline all the way upstream to the raw ingestion phase. The action we are tracking is a specific sub-millisecond sequence, a targeted mouse double-click, immediately followed by the execution of a Ctrl-Alt-T hotkey. What precise physical, mathematical, and memory-level computations had to occur in the milliseconds prior to that hardware actuation? Between the moment the model processes a visual token and the KVM executes a click, there is a rigid, zero-tolerance data pipeline. The absolute end of the Pi IntelliJet VLM pipeline is a REST API dispatch sent directly to the JET KVM hardware device. This mockup shows the central state ledger. It is an append-only historical trace that maps a human-readable intent down to strict USB HID keycodes. You can see the mapped protocol payload and the command's exact latency measured in milliseconds. The ledger translates our Ctrl-Alt-T hotkey sequence into literal structural keycodes, Ctrl-Left, Alt-Left, and Key-T. The target machine registers this payload exactly as if a human pressed those keys on a physical keyboard. Just above the hotkey execution, the payload records the mouse action, dictating the exact absolute pixel coordinates required for the double-click. A neural network does not naturally output high-resolution absolute screen positions. We have to determine how the VLM accurately derived precise spatial coordinates for a 1080p screen. While the ledger proves a physical action was successfully dispatched, the safety of that action relies entirely on the accuracy of the coordinate mathematics executing one step upstream. Stepping backward in the pipeline, we arrive at the coordinate scaling translation layer. The target machine operates in a raw screen space of 1920 by 1080 pixels. The neural model, however, ingests a heavily downscaled 448 by 448 matrix space. This animated diagram illustrates the normalized ratio transformation equations, bridging the disparate scale spaces without allowing coordinates to drift. The math extracts normalized ratios, Rx and Ry, representing relative fractional positions, then strictly clamps them to the active screen boundaries. Before any HID command is authorized, it must pass through a server-side pixel parity validation gate. The system calculates the Euclidean pixel error distance to detect even the slightest coordinate skewing between the model's output and the raw screen space. The rejection parameters are strict. If the Euclidean error exceeds a 2.0 pixel threshold, the backend drops the action entirely. Mathematical parity serves as the ultimate failsafe. It guarantees the VLM cannot execute errant or destructive clicks outside of validated UI elements. Moving backward again to the inference execution layer, the system has to generate these complex coordinate mappings fast enough to beat the hardware actuation timer. Traditional vision language pipelines suffer from a severe latency penalty. Copying raw frame buffers back and forth across a PCIe bus, from system RAM to discrete GPU VRAM, consumes critical processing time. This split screen compares the traditional approach against our hardware solution, the Intel Core Ultra 9 288V Lunar Lake, and its unified memory architecture. Using OpenVINO GenAI, Pi IntelliJet VLM implements zero-copy tensor wrapping. The system directly wraps the array into a shared memory address, eliminating copy overhead entirely. This shared memory space instantly feeds the 4-bit quantized multimodal Gemma 4 weights executing on the integrated ARC140V graphics unit. Eliminating the PCIe memory transfer is the precise engineering optimization that unlocks the sub-millisecond time-to-first token necessary for live robotic control. Now we reach the absolute beginning of the data pipeline, capturing the real-time HDMI video stream from the target machine. High-resolution hardware streams running at 60 frames per second present a logistical danger. If fed directly into the pipeline, they will instantly overflow the zero-copy neural processing queues. This diagram shows the defensive engineering layer, a 5 frame per second rate-limiting ceiling backed by a latest frame buffer container. It functions as an O(1) memory container working natively in Python, strictly holding only the latest available frame. The system enforces a 200 millisecond threshold rule. If frames arrive faster than the VLM can process them, they are structurally dropped without allocating any new memory. Before entering the buffer, these frames can undergo region of interest cropping to isolate specific spatial UI elements, like terminals or editor panels, further reducing the neural load. Aggressive, structured frame dropping is not a limitation, it is a mandatory architectural safeguard ensuring deterministic execution speed downstream. With the reverse trace complete, we can view the entire PyIntelliJet VLM architecture operating in its natural forward flow. Hardware ingestion hits the O(1) buffer for rate limiting. That data feeds directly into zero-copy inference on the LPDDR5X memory bus. The output undergoes sub-millisecond parity validation and finally triggers physical actuation via the JET KVM. Building a reliable autonomous agent requires one final element: operational stability over continuous, long-running execution loops. This terminal layout shows an end-to-end stress test simulation sequence running on Python 3.14. It utilizes any I/O structured concurrency task pools to manage the workload. This strict lifecycle management prevents thread leakage and lingering coroutines from destroying the agent's memory footprint during sustained hardware automation. While vision language models provide the core intelligence, true autonomous graphical interaction depends on the structural elimination of memory bottlenecks and the mathematical enforcement of spatial parity at the hardware edge.